Sorry, I'm trying to figure out Zoom on my cell phone.
That's okay.
Linda, would you like me to wait until Brian comes back?
No, he said we can go ahead and
Okay.
talk about things and yeah, I'll wait
Okay.
till I'll introduce him when I see him.
Okay, because I just have a couple of quick announcements. Some of you who are members should have gotten the email. Our next Observing Basics class number 3, which is going to be about setup and operations of astronomical telescopes and binoculars. If you haven't seen the first 2 classes, they are available for viewing on our website. And they are about observing basics. And our 3rd class, will be Tuesday, August 24th at 7 p.m. We will be live streaming it on Zoom as well as Facebook and YouTube. And then if you miss the class, it will be available on our website. And then the 4th class, which will be coming probably in a month or a month and a half, will be about astrophotography. So I'm very excited about those next 2 classes, which are put on by our vice president. And then next year is the 70th anniversary of the SFAA. That's a big one. So we are asking if any members have any photos or stories or would like to share any history of the club, that they please email telescopes@sfaa-astronomy.org. That is one of our directors, that is Douglas, and he is handling the collection of our history. So, and you can also always email me, which is just president@sfaa-astronomy.org. And that is if you have any photos, if you have any funny stories, photos of members from star parties or lectures. We just want to collect all the wonderful history of all the past 70 years. So with that, I will hand it over to Linda.
Okay. I just wanted to mention to those of you who may be meeting with us for the first time, we always meet on the 3rd Wednesdays each month at this point, 7 p.m. on Zoom. So we welcome you to join us in the future. And the next talk is on September the 15th. It's called Shooting the Stars, Tales from the Stratosphere. It's by Marita Beard, who's a physics instructor. SOFIA, which is NASA's Stratospheric Observatory for Infrared Astronomy, offers teachers the opportunity to experience firsthand what it's like to be aboard the modified Boeing 747. There's a 106-inch telescope on board and many other special instruments for viewing in the infrared light. Flying into the stratosphere as an airborne astronomy ambassador. As an AP physics teacher, Marita feels she has much to contribute because of her work with SOFIA at NASA prior to going into teaching. So she'll give us a very interesting talk on that. Then on October the 20th, Living with a Star, the Sun, Space Weather, and Our Place in the Solar Neighborhood by Dr. Phyllis Whittlesey from UC Berkeley's Space Sciences Lab. As humanity expands its presence on the moon and Mars, we will venture outside of Earth's protective magnetic bubble. And on Earth, we also feel, of course, the effects of space weather. Several currently operating and future NASA and European Space Agency missions seek to uncover persisting mysteries about our sun. Dr. Whittlesey is an instrument lead for instruments aboard the Parker Solar Probe, which is orbiting the sun, and it was launched in 2018. And she's currently also leading instrumentation on 2 of NASA's Heliophysics Division's missions that are now in development. So I'm happy we're going to have a space weather talk October the 20th. And I'm so happy tonight that we're going to find out how our family can land on Mars and explore the solar system with NASA Solar System Treks. Brian Day received a bachelor's degree in psychology from UCLA and a bachelor's degree in information systems at UCSF, then a master's in astronomy from the University of Western Sydney. He works at NASA's Solar System Exploration Research Virtual Institute, where he serves as lead for lunar and planetary mapping and modeling. Has participated in various Mars analog field studies in extreme Mars-like environments here on Earth. He previously served as education and public outreach lead for the L-Cross and LADEE robotic missions on the moon. 2007, he flew on NASA's Origid MAC mission to record debris from comet Kais, which is burning up in Earth's upper atmosphere. Brian Day is about to land us on Mars Jezero Crater, and that's just the first of the many, many places that he will take us on our trek in the solar system. So I'm so happy you're here, Brian, and we are so happy that we get to have a wonderful tour. Thanks to you.
All right. Well, thank you very much, Linda. It is a great pleasure and honor to be talking to the SFAA again. This is a wonderful organization, and I always enjoy meeting with you. So I'm going to attempt at this point to share my screen, and with any luck here, you will now see my opening slide. Yep. So we're going to tour the solar system tonight, and we're going to do that using a suite of online tools, the NASA Solar System Treks. And by the end of tonight, I hope to have you hooked on these online tools, and I'll show you basically how to use them. But for now, what we'll do is we'll just use these portals to start out, and by popular demand, we're going to start with Mars. So this is how Mars would appear if you were looking out the window of a spacecraft. This is actually Viking orbiter data. And with this, we can see that Mars today is in fact a complete and total desert. But if we change our view, look at this same perspective, but using a different instrument, now we'll use the Mars Orbiter Laser Altimeter, we get a very different concept of what's going on Mars. Here we're looking at altitude differences. We're color coding different altitudes. Blue is low, red is high. And when we use this instrument to look at Mars, we get some very interesting insights. We see that Mars was not always a complete desert. We see clear signs of ancient riverbeds where rivers once flowed into what appears to be a large bay that then emptied into what was apparently a great northern ocean on Mars. If you were looking at Mars 3.5 to 4 billion years ago, you would have seen a very different place, a place with water flowing across the surface, with rivers, an ocean, and lakes. Looking more closely at some of these river channels, you can see how water carved and streamlined the terrain. It doesn't take a lot of imagination here to imagine the water flowing from left to right in this view. Now, one of the places back then that definitely was a site of water and is attracting our interest now is a place called Jezero Crater. And here's a view of Jezero Crater. It's a fairly degraded crater. It's old. It's about 3.8 billion years old or so. And it's about 45 kilometers across. But what we can see here is we can see that along its west side, we can see one of those river channels coming in. We can see another river channel coming in from the north. And we see another river channel off here on the east. And if we were to look here between 3.5 to 4 billion years ago, we would have seen a large crater lake. Water flowing in, nearly filling the crater and sometimes overflowing the crater. And we even had an outflow channel. So looking more carefully at Jezero Crater, we can map out some of its key features. The center of the crater we've got marked here as A. B is the landing ellipse for our current Perseverance rover. That's where it is right now. Looking over here on the western edge of the crater, we can see a delta deposit labeled C here, where water came in through this river channel through a breach in the crater rim and the water dumped its load of sediment onto the floor of the lake. We can see another delta deposit here on the north, where another river channel flowed in from that direction. And then we have an outflow channel here on the east. So we see similar features to these deltas here on Earth. This is the Nile Delta, and so you can see where the flow of the Nile, as it reaches the Mediterranean, the water slowed as it entered the water of the Mediterranean, and it dumped its load of sediment, forming this triangular shaped delta deposit. And here we can compare that to the delta deposit on the western side of Jezero Crater. And when we think of the fact that this water was gathering material from a time when Mars was at its wettest and most habitable, it was gathering that material from a vast watershed to the west, and it was concentrating it, bringing it in, and dumping it all right here at this one place. If you're an astrobiologist, this is the exact kind of mud pile you want to play in. So let's take a look at the general context of Jezero. It is on the edge of the Great Ceres major volcano off here to the left. And you can see the actual landing site of Perseverance labeled there in the crater. And what we'll do is we'll just progressively zoom in a little bit here and note, again, near the delta deposit where Perseverance landed. As we continue to zoom in, we now start seeing individual sand dunes. The spacecraft was smart enough not to land in the sand dunes, but off to the side. And now we'll change our perspective, looking out from the landing site, looking out to the cliffs of the delta deposit. And in the background, these mountains are the actual rim of Jezero Crater. Let's look a little more closely now at the actual strata of the delta deposit. And again, this is actual data. This is not an artist's conception. This is actual data coming back, in this case, from the Mars Reconnaissance Orbiter. And we're able to reproject it to get to any angle we want. Here we can see the breach in the crater wall through which the river flowed. And we can even follow the course of the river. And again, notice the sand dunes that are now inhabiting the floor of this riverbed. There are many other areas of great interest on Mars. Another fantastic landmark is, of course, Valles Marineris, Mars's Grand Canyon. And when I say grand, I mean really grand. If this were placed here on Earth, it could stretch all the way from San Francisco to New York. 600 kilometers across at its widest. And the walls of the canyon tower some 8 kilometers tall. That's the height of the Himalayas. So this is truly a magnificent canyon. Spectacular landslides adorn its walls. This was not formed by flowing water like our Grand Canyon. This is a great tectonic rift, probably triggered by the mass of the giant volcanic Tharsis bulge to the northwest. And here we'll take a interactive flight into Valles Marineris, flying over the ridges and sand dunes and the sedimentary deposits on the floors of ancient paleo lake beds. This will be a spectacular place for astronauts to live and work in the future. So I mentioned the Tharsis bulge. This is one of the great volcanic areas of Mars, where we have a number of volcanoes and really immense volcanoes. Even the smaller volcanoes on this image here like Uranus, Tholis, would be considered giants here on Earth. But the one that really dominates is, of course, Olympus Mons. And here we see a view of Olympus Mons. It is a true giant. It's 624 kilometers across. Here's a laser altimetry view, gives us a little bit of a better perspective. It stands 25 kilometers tall. It's approaching 3 times the height of Mount Everest. If you think of, perhaps you've looked at a map of Washington State, and you're familiar with Mount Rainier in Washington. And Mount Rainier is, of course, the greatest of the volcanoes in Washington State. It is truly magnificent. But when you look at a map of all of Washington State, Mount Rainier is but a dot on that map. If you were to put Olympus Mons on that same map, it would cover almost the entirety of Washington State. This is a monster of a volcano. Here, looking down at the summit caldera, you know, this volcano has a lot in common with the great shield volcanoes of Hawaii, but the thing that differentiates it is its size. You could put the entire island of Oahu inside this summit caldera. And looking at it in profile here, you see that it is, in fact, a long, low profile shield volcano. So in form, it does look very much like the volcanoes you might see in Hawaii, like Mauna Loa, but it is far different in size. Oops. There are other volcanic areas. Here we see the volcanoes of the Elysium area, including Elysium Mons. Again, true giants. And just south of the Elysium volcanic area, we come to the Cerberus fossae, these great faults, magnificent crustal fractures in the crust of Mars, just really spectacular. And the Mars InSight lander, which is a robotic geologist, has been doing seismic studies of Mars, and it has actually detected Mars quakes coming from these faults right here. So this is an active seismic area on Mars. Really spectacular terrain, and using our Mars Trek portal, you can fly along and down into these fissures. But these are areas of great interest. When we look at the volcanic features of Mars, we see volcanoes that are typically hundreds of millions to billions of years old. But here along the Cerberus fossae, we see lava deposits that are only a few million years old. And that really gets our interest. And then there's this, the Cerberus fossae mantling unit. You can see just above and to the left of Gale Crater, you can see the great crack in the ground and that kind of darkened area around it. That is an ash deposit. That's volcanic ash from an eruption that has been dated as probably only 222,000 to as young as 46,000 years old. That's incredibly recent. That, you know, in terms of geologic time, that is really recent. And that makes us wonder, could Mars still be volcanically active today? Now take a closer look at Gale Crater in the lower right. It is surrounded by a really pasty ejecta blanket. This is typical of features we call rampart craters. Craters that were formed by impacts in areas that have rich supplies of subsurface water or ice. And so you can imagine the impact that caused this crater causing a great sploosh of wet material to be ejected around the surface. Now, Jezero Crater here is young. It's only 2.7 million years old. And so we think that perhaps the formation of that crater may have something to do with the volcanic activity near it. It may have, the formation of this crater, the impact that formed it, may have fractured the crust in a way that allowed magma, deep magma beneath the crust of Mars, to come up through those fractures and then interact with that layer of ice that we see evidence for in Jezero. As that magma hit that subsurface ice, it would have flashed into steam, causing what we call a phreatomagmatic explosion, or a charged eruption of lava mixed with water vapor that would have blasted this ash out over the terrain. So this is a very, very interesting area. Also, as we look across lava flows, in addition to impact craters, we see another type of hole in the surface. We see these pits that are apparently skylights, where the roofs of subterranean lava tubes have collapsed. So imagine these vast caverns beneath the surface where lava once flowed. And now those have been evacuated to form hollow caverns, and in places, the actual roof collapses. If you go to Hawaii, again, you can journey through lava tubes, or you go up to Northern California to lava beds. They're wonderful examples. And we see these here on Mars. These could be places that are of great interest to us. Some have proposed that this could be a good place for human settlements. They'd be protected from micrometeorites, from radiation from the sun, from wild swings in temperature. If you do, in fact, have subsurface water, this could get you close to it. But these could also be places that we would want to go to look for perhaps residual life that might still be on Mars. So when we end up living and working on Mars, water is going to be a critical issue. And of course, there is water at the polar ice caps. But the polar ice caps is someplace we just don't want to send our astronauts. It is really too extreme an environment. Mars is pretty tough anyway, but you get to the poles and it gets really, really rugged. But fortunately, it turns out that there are bands of mid-latitude glaciers located at approximately 40 degrees north and 40 degrees south. And these glaciers are still existent today. They are what we call debris-covered glaciers. They're covered with dust and sand and gravel, but they still do cover significant deposits of water ice. And we can tell that from ground penetrating radar flying over them. And so we now realize that if you were to take all of the ice in these mid-latitude glaciers and distribute it over the entire surface of Mars, you'd have something over, probably a few meters of coverage of ice over the entire surface. So there's a significant amount of water here. So here you can see a fine example of a valley glacier. Here's another example of a valley glacier. We're flying in much more closely. If you've ever flown around in Alaska, this type of thing will look familiar to you, with medial moraines and flow features. Here we see, well, here on Earth, we would call a Piedmont glacier, this big toe-shaped feature. We can zoom in a little more closely and get a look at that glacial toe there. Another type of glacier that we find on Mars are the lobate debris apron glaciers that oftentimes surround mountain peaks. Here you can see all these beautiful glacial ridges and even a large Bergschrund crevasse where the ice is pulled away from the face of the mountain. We also see concentric crater-filled glaciers. Craters can be excellent places for glacial ice to accumulate. And this is one of my favorite places. I just stumbled upon this while using Mars Trek to fly around the surface of Mars. And here we see another example of one of these low rampart craters. So this crater was formed by an impact in an area that had abundant water or ice beneath the surface. You got this big sploosh of mud. If you look very carefully, you'll see these fluvial features of water that actually went flowing out across the surface from the impact. But then here, afterwards, you have this front of a glacier advancing, and you can tell the glacier is clearly younger than the impact because the glacier is actually overriding, going on top of the actual impact debris apron there. So a lot of interesting stuff. And there also appears to be some accumulation of glacial ice inside the crater. Lots of interesting stories to be told. Now, looking back at this ancient ocean, maybe 4 billion years ago on Mars, we see the depression, the basin that filled it. It's full of sedimentary deposits now. But one of the really interesting clues to its existence are mega tsunami scars, areas where you would have impacts, asteroids crashing into the surface of the ocean and causing tsunamis that would be huge. I mean, these are the types of things where they could rush inland by hundreds of kilometers, and they could be 300 meters tall. So just really titanic tsunamis. Looking closely here, we see what we would call thumbprint terrain. And this is chaotic terrain caused by reflection and refraction of turbulent water around the existing land features as the water rushed inland. And then we see backflow channels where the water flowing back across the terrain back toward the shoreline of the ocean. And as it flowed back, it carved these channels. Really fascinating stories. But right now, a lot of our attention is being focused on the moon. And for good reason. We're planning to return to the moon and doing so in a sustained manner. So we have the Artemis Program, and the idea is to bring, in the next few years, the first woman and the next man to walk on the surface of the moon. And in addition, we're going to have a number of precursor robotic missions that will be landing on the moon starting next year. So where are we looking to go? One of the places that really has our interest is the South Pole. And using our Moon Trek portal, we can zoom into the South Pole. And we can see that this is an area, because the sunlight is coming in nearly horizontally, this is an area of deep shadows. In fact, there are areas here in craters near the pole of the moon where the sunlight has not shone in well over 1 billion years. That makes these the coldest areas we've measured yet anywhere in the solar system, even colder than the surface of Pluto. And in some of these dark shadows, we have discovered that there are deposits of water ice. But these shadows make it really hard to ferret out what's going on. But fortunately, we can switch to a laser altimetry view, and we can use that to pierce the shadows and see the actual terrain inside these craters. We can use that laser altimetry to generate slope maps that help us plan our upcoming traverses. We can then overlay the areas where the shadows are truly permanent. These areas that we might want to pay special attention to, looking for resources such as water ice. In Moontrek, you can look at things such as average temperature and maximum temperature to again help you to zero in on areas of active interest. We can look at albedo from the LAMP instrument to see areas that may actually be indications of surface frost accumulating right exposed in some of these very dark areas. We can do neutron spectrometry, looking for concentrations of hydrogen as markers for the appearance of water. And what we're doing here is we're looking at the same view just through the eyes of different instruments, georeferenced co-registered data products. Here we see a map of ice stability at depth. How far would you have to dig down to get to a temperature where ice could remain stable? And in some of those permanently shadowed craters, you don't have to dig at all. So the South Pole is an area of great interest. This is where we will be sending a number of our robotic missions, and this is where we will be sending our crewed missions of Artemis. But before that, we're going to have some robotic missions going to some other areas. One of the first will be the area of Lacus Mortis, which is very visible in your own telescopes. I encourage you to look at it. Here it is in the northeastern quadrant of the moon. Zooming in, we can see that Lacus Mortis is an impact feature, a large impact feature, about 3.8 billion years old. And it measures, about 159 kilometers or 99 miles across. You have the crater Berg inside of it. Berg has this beautiful landslide on its coming from its western rim. But if you look at the floor of Lacus Mortis, you see these incredible networks of straight rills where the floor has fractured due to magma rising up through the crust and wedging the crust apart. If we zoom into this area here, this southwestern portion where one of those rills meets the crater rim, we see actually examples of two lunar volcanoes. These are lunar domes. You can see the small actual volcanic craters at the summits of both of these volcanoes. Clearly an interesting area. And also on the floor of Lacus Mortis, we have a pit that again is a skylight into a subsurface lava tube. So this is going to be a very fascinating area for us to explore. Ideally, we'll be landing next year, sometime early in 2022. Another place we have targeted is Dorsum Arduino, which is kind of on the border of Mare Imbrium and Oceanus Procellarum. And as we zoom in, we see that this is actually an example of a wrinkle ridge. You can see it here. This is something you would be able to pick up in your telescopes under low angle of lighting. You'd want to have the terminator very near this area. Again, using laser altimeter, it stands right out. Another area we are targeting is Reiner Gamma, a popular target for amateur astronomers, located right on near the western limb. This is an example of what we call a lunar swirl. It is an albedo feature. It doesn't have any topography. It is a flat area, but we see this intricate interplay between light and dark. This also corresponds to an area of a localized magnetic field. The moon does not have a global magnetic field, but it does have areas of remnant localized magnetic fields, and this is one of them. And we think what possibly is happening here is that local magnetic field is channeling the radiation as it comes in from space and impacts the surface. and causes different degrees of space weathering. The light areas are relatively protected. The dark areas are where radiation gets focused. What causes this localized magnetic field? We don't know. So that's one of the reasons we want to go here and explore. Another one of our targets is the Mare Crisium area. Again, this is something you are probably very familiar with. It is visible to the unaided eye and is great in telescopes and binoculars. Zooming in with the Moon Trek portal, we see a beautiful example of a cinder cone that is breached to the south. This has been given the nickname Horseshoe Crater, and it is our intention to land just off to the side of this volcanic peak. Schrödinger Basin is one of our more ambitious targets in the next few years. This lies on the far side of the moon. As we look at the far side of the moon down toward the south, you have the South Pole Aitken Basin, which shows up as this large blue depression here. This is the largest and oldest impact basin we know of on the moon, something over 4 billion years probably, and it measures about 2,500 kilometers across. On the edge of the South Pole Aitken Basin, you have a younger crater, Schrödinger, that measures 312 kilometers across, and it excavated into the edge of the South Pole Aitken Basin. Zooming in, we can get a closer view of Schrödinger. It's really a magnificently complex place. You have mare deposits within it. You have raised rims. You have exposures of bedrock. You have fractures, much like what we saw in Lacus Mortis. And along one of those fractures, we see this beautiful volcanic pit with a dark blanket of volcanic ash around it. And inside the volcanic pit is a permanently shadowed region. And here's a closer view of that volcanic pit. Now, the Gruithuisen domes are also on our list of targets, and they're examples of lunar volcanoes. Now, here are typical examples of lunar volcanoes. These are the Hortensius domes. Lunar volcanoes, lunar domes, tend to be very low profile shield volcanoes, maybe about 8 kilometers across typically, with very, very gentle slopes. A couple degrees to a fraction of a degree. They are very low profile because of the fact that in general, lunar lava, when it erupted, had a very low viscosity, similar to olive oil at room temperature, and it's hard to build a mountain out of that. So when you go looking for lunar domes, you really have to do it when the lighting is extreme, when you get the terminator right near the dome so that every little bit of shadowing will work for you. But then there are exceptions. These are the Gruithuisen domes. And again, these are quite visible in your telescopes. These are lunar volcanoes that stand out. These are tall. They get up to 1.7 kilometers tall with steep slopes. These are big, steep volcanoes. And that's because the lava here has a much higher silica content. And therefore it was thicker, more viscous, pasty when it erupted. The question is, why was lava here so much different? We don't know. That's one of the reasons why we want to go explore this area. You can again see the rather spectacular terrain of the Gruithuisen domes. Now we'll jump to the planet Mercury. And Mercury was visited by the Messenger spacecraft. And it showed us that the surface of Mercury is covered with craters. It looks very much like the moon. Here we're looking at the large crater Rachmaninoff, a multi-ring impact basin. We can see how with the Mercury Trek portal, we can actually measure the elevation profile of this crater. One of the greatest impact basins, or the greatest impact basin on Mercury, is Caloris. It measures 1,500 kilometers across, and it was filled with magma, with lava that erupted from fissures. And as we look at the center of Caloris, we see this magnificent network of cracks streaming out from Apollodorus crater. And it almost looks like the impact that formed Apollodorus cracked the surface of Mercury like an egg. But that's actually not what happened here. It turns out this is a chance alignment. The fractures here of the Pantheon fossae are actually significantly older than Apollodorus crater. And what we see here are examples of extensional tectonism, the crust spreading and cracking. Now, one of the really interesting things is if we look on the other side of Mercury, we see this strangely jumbled terrain here. It's called weird terrain. It was named without a great deal of imagination, but it's this really hard to explain jumble. What would have caused features like this? And that was a mystery until people realized that this area is exactly antipodal, exactly opposite of the Caloris Basin. And so when that impact, that giant impact that formed Caloris happened, the shock waves traveled across the globe of Mercury, spreading out, but then reconverging exactly opposite Caloris. And the disruption that formed by that focusing of shock waves broke up the terrain here, forming this really unique landscape. As we look across Mercury, in addition to impact features, we see these irregular craters. These are volcanic pits, and oftentimes they are surrounded by blankets of volcanic ash. Mercury exhibits a great deal of volcanic terrain. As we look at a number of the impact craters, we see these strange-looking deposits on their floors. These were originally called bright crater floor deposits. As you look more closely, they're networks of hollows, little pits. And what seems to be happening here is that the extreme temperature on Mercury, this is the closest planet to the sun, and temperatures get up to 430 Celsius, 800 degrees Fahrenheit, and you can start vaporizing some of the minerals. And so what you see here are areas where some of the minerals have that were exposed in the formation of the crater have then actually been boiled off into space. Mercury is clearly a very hot location because of its proximity to the sun. But as we look at the poles, again, we find areas that have permanent shadows. And much to our surprise, when we first started looking into these shadows, we found deposits of water ice. So even on this inferno of Mercury, there are deposits of water ice at the poles. Next, we'll move to the dwarf planet Ceres. And Ceres is a small world, about 946 kilometers in diameter. It was visited by NASA's Dawn mission, which orbited Ceres actively from 2015 to 2018. And one of the first things it saw as it approached were these two bright spots in this crater that has been named Gale Crater. And these drew a great deal of interest. You know, what in the world could they be? And as we look more closely at these features, we see that these are actually deposits of salt. And these are apparently the remnants of cryovolcanism. On Ceres, the role of magma is played by a slushy, icy salt water. And you can think of volcanism here as being water-based rather than silicate-based as it is here on Earth. So imagine eruptions of briny water coming up through fractures in the floor here of the crater, and the water turning to vapor, to gas, disseminating out into space, but leaving behind the deposits of salt. An even more spectacular example of what we call this cryovolcanism occurs in an area known as Ohuna Mons. This is a cryovolcano. And this is a big mountain. It stands 4 kilometers tall. Notice how fresh and uneroded the slopes are. This is a young feature. But it's also a feature that perplexed us, because as we look across the entire surface of Ceres, we don't see anything else that looks like this. And that makes us wonder, why would the formation of volcanoes like this be something that we only see now? Why would that be something that's just happening now? Why wouldn't that be something that extended back into the past? What's going on here? Well, it turns out there are other cryovolcanoes. This was discovered just as we were putting together this Ceres Trek portal. Close to 24 of these volcanoes were found, but they're very low, shallow, pancake-shaped features. We call these relic cryovolcanoes, because in the thermal and gravity environment of Ceres, a big mountain of ice over time will deform elastically and flatten out. And so here we can see an example of an older volcano inside Gale Crater. And again, using the tools that are available to you in the solar system treks, you can actually explore the elevation profile, measure the topography of these ancient craters. Another relic cryovolcano lies very near Ceres' North Pole. This is Yamor Mons. The Samhain Catani are vast rifts across the crust of Ceres. And this is an area of active spreading where the crust is being driven apart. We think what's happening here is that material rising from the mantle, rising up in a plume, striking the crust, spreading out, and dragging the crust along with it, causing this localized spreading. This gives us clues that within the mantle of Ceres, we think there is an ocean of liquid water. Ceres, located between the orbits of Mars and Jupiter, could be another ocean world in our solar system. The Dawn mission also visited the asteroid Vesta. Vesta measures 572 kilometers across. That's big enough that when it formed, gravity should have pulled it into a nice, beautiful sphere. But if you look at it here, it doesn't look so spherical. Well, the top of it looks pretty good, But as you get down here toward the South Pole, it almost looks like part of the world is missing. And that's exactly the case. If we look right down at the South Pole, we see a large impact crater here. This is the Reyes Sylvia impact crater, measures about 500 kilometers across. Now, for a world that has a diameter of 575 kilometers, this is a big thing. And then if you notice, it's overlapping an older but similar sized impact. This is the Venenia Basin. We estimate Reyes Sylvia about 1 billion years old, Venenia about 2 billion years. And so two nearly fatal impacts nearly destroyed Vesta. The central peak in Reyes Sylvia is really spectacular. This is a gigantic mountain. This stands 22 kilometers tall. That's almost as tall as Olympus Mons on a tiny little world that is only 575 kilometers across. Circumferentially around Vesta, you see these fractures, the Devalia fossae, that are centered on the Reyes Sylvia Basin. And these show us how Vesta was very nearly destroyed by the impact that caused those, the impacts that caused those basins at the South Pole. As a matter of fact, we see a trail of debris through space, small fragments of Ceres, or of Vesta, excuse me, small fragments of Vesta, little tiny asteroids that we call vestoids. They have the same spectral fingerprint as Vesta. And that trail of debris even makes it all the way to the Earth in the form of the Howardite, Eucrite, and Diagenite types of meteorites. And so we have those pieces of Vesta landing here on Earth, shards from this dramatic collision. As we look across the terrain of Vesta, we also see areas of pitted terrain, clusters of rimless pits, oftentimes located near impact craters. And what this appears to be showing us is areas of where, even though Vesta is an intensely rocky world, there were deposits of water ice or ices of various types beneath the surface. And when the heat from local impacts reached those areas, it caused those ices to flash to steam, which expanded explosively, causing these eruptive pits to form on the surface. Continuing our look at asteroids, we'll go to the asteroid Bennu, which you'll remember from the news was recently visited by the OSIRIS-REx mission. And OSIRIS-REx is currently on its way back with samples collected from the surface of Bennu. As a matter of fact, we can use our Bennu Trek portal to fly down and look at Gale Crater, where Bennu actually touched down and collected samples. But also, OSIRIS-REx found something really interesting. The rocks, the intensely bouldered terrain of Bennu is typically populated by a very primitive carbonaceous type of rock. This is some of the earliest, most pristine type of building blocks of the early solar system. But here and there, we see boulders that stand out, that look very different, that just don't fit. And these actually show up as being basaltic in nature, a type of lava rock. And as a matter of fact, their spectral signature matches very, very, very closely what Dawn saw on Vesta. So it appears what we are seeing here on Bennu are actual pieces of Vesta that have landed on the surface there. A similar object is the asteroid Ryugu. And Ryugu was recently visited by the Japanese Hayabusa 2 mission. And just this last year, Hayabusa 2 returned samples from the surface of Ryugu. Both Ryugu and Bennu look very similar to each other. They have this strange kind of top-shaped appearance. They are rubble piles. They are not solid bodies like we've been looking at so far. They are very loosely held together piles of cosmic boulders, shattered remains from ancient collisions. Bennu is only 490 meters across. It's a small world. Ryugu is a bit larger, but still small at only 870 meters. But these are important for us to monitor because these are both near-Earth asteroids. These are asteroids whose orbits actually cross the orbit of Earth. And so these types of objects are ones that were important for us to visit, to understand, and to continue to monitor. Now we're going to take a big step out. We're going to go to the Jovian system, and this is Jupiter's moon, Europa, one of 79 currently counted moons around Jupiter. Europa measures 3,120 kilometers across, just slightly smaller than our moon. It is covered by this global crust of ice. And as we look closer, we see that it is a very fresh looking terrain. You see a remarkable absence of impact craters, but you see evidence of a lot of activity. You see ridges where new material is apparently welling up from inside of Europa. You see chaotic terrain here that we'll look at more closely, but all of this is telling us a story that there's a crust of ice that overlies an ocean of liquid water. And as a matter of fact, the ocean of Europa, in terms of volume, totals approximately twice that of all of Earth's oceans combined. As we zoom in on that chaotic terrain, we can see ice rafts. One of which here, you can see how it was actually pushed up and upended. So it seems to be sinking down into something beneath. This is clearly not a really solid crust. Now there's a debate going on as to how thick this ice crust of Europa is. Some say that it is actually quite thin, only a few kilometers. And in places like here, the chaotic terrain, that ocean nearly breaks through to the surface. Others cite models where the crust could be much thicker, tens of kilometers or more, perhaps considerably more. And in which case, perhaps these chaotic terrains represent areas of ice rafts on top of subsurface lakes that are well above the level of the ocean beneath. We're not sure just what's going on here on Europa, but we know with that much water, we're drawn to explore it. Because here on Earth, wherever we find liquid water, we find life. And people can't help but wonder if in the ocean of Europa, there could be life. And so looking ahead, we have the Europa Clipper mission scheduled to go explore Europa in greater detail. Moving out to the Saturn system, we have Saturn's greatest moon, Titan. Titan is a large body. It measures over 5,000 kilometers across. And it is the only moon in our solar system that has a thick, dense atmosphere, even thicker and denser than the Earth's. That makes it hard to see the surface. But the Cassini probe, carrying with it the Huygens lander, explored the Saturn system between 2004 and 2017 and did a number of flybys of Titan, giving us some tantalizing looks. We see that beneath that hazy atmosphere, there are river channels and lakes and even seas populated with chains of islands. But these are not bodies of water. The temperature here is very, very low. This is minus 179 Celsius, or about 290 degrees Fahrenheit below zero. So these liquid bodies here, these aren't water. This is actually lakes and seas of liquid hydrocarbons, mostly methane and ethane. But we now realize that beneath this icy crust of Titan is a subsurface ocean of liquid water. Now, astrobiologists have come up with interesting ideas how conceivably, even in these frigid oceans of hydrocarbons, there could be exotic ways for life to come into existence. You could have very different types of life than water-based life here. This would be a hydrocarbon-based life. But then beneath the crust of Titan, again, you have an ocean of liquid water. So perhaps down there you could have life more similar to us. Clearly, Titan is a fascinating world. It's one we're drawn to explore. And we have missions planned to go there, including a drone that will fly across the surface of Titan. It's called the Dragonfly mission. It's being prepared to go to Titan. Also in the system of Saturn, we have another portal called Icy Moon Treks. They give us views of 7 of Saturn's smaller icy moons. And they are fascinating worlds in and of themselves. Probably the standout is Saturn's moon Enceladus. And in areas we see, across the surface, we see a very diverse terrain. We see some areas that are clearly older and covered with impact craters, but we see some areas where the impact craters have been erased, where the surface has been repaved by active geologic processes along great rifts crossing the surface here, ridges and cracks. Clearly there's something dynamic going on. As we look at the south pole of Enceladus, we see this spectacular network of fissures named the tiger stripe fractures. These are especially dramatic rifts in the icy crust of Enceladus. And we now realize that, similar to what we saw Europa, beneath this crust of ice, we have an ocean of liquid water. And that is not just speculation, because we see from these tiger stripe fractures, we actually see geysers of water erupting out into space. We actually flew the Cassini spacecraft through them, sampling them. And the water is rich in salts and organic molecules. And recently it was noted that there is a high concentration of methane that doesn't seem to match the signature that we would expect from a geologic source, like perhaps we see on Titan. Here on Earth, when we find methane, it is often associated with biological activity, and there is considerable speculation right now that the amount of methane that they're seeing in these geysers erupting into space is perhaps more consistent with biological activity. So this is a world that really has our interest. Another one of Saturn's moons is Dione. Dione presents, again, very dramatically different faces. The leading hemisphere, as it moves in its orbit around Saturn, looks almost lunar, a very intensely cratered, older terrain. But if you look at the trailing hemisphere, you see great ice ridges in areas where, again, the surface has been repaved. We now understand that Dione is also an ocean world beneath a somewhat thicker crust of ice than what we see in Enceladus. There is, again, apparently an ocean of liquid water. The moon Rhea stands out because its leading edge is remarkably brighter than the trailing edge. This stands in direct contrast to Saturn's moon Iapetus, where the leading edge is significantly darker than the trailing edge. And you can actually see these features through your telescopes. If you look for these moons, you'll see that they will be much brighter when they are on one side of Saturn than the other, even though you will not be able to resolve the disks of Iapetus or the other moons, but you will be able to see the dichotomy in brightness between Rhea and Iapetus' leading and trailing edge by looking at the difference in brightness when the moon is on one side of Saturn versus the other. The moon Tethys clearly had a very bad day. This is the giant crater Odysseus. The impact nearly destroyed Tethys. Similarly, Mimas had another bad day. The crater Herschel gives this a look that closely resembles the Death Star from the Star Wars movie. And then, somewhat different than any of the moons we've looked at so far, this is the moon Phoebe. It is one of Saturn's outer moons. So Saturn has 82 moons at last count, probably many more. But this is one of the outer irregular moons. It orbits in a retrograde motion at a high inclination. It's very, very dark in albedo. It resembles what we've seen in some of the comets we've gotten a close look at. A mixture of ice and dark carbonaceous rock. And its size, its strange orbit, its composition have led many to suspect that Phoebe is actually a captured Kuiper belt object that fell into the inner solar system and got snagged by Saturn's gravitational pull. So all of the views that we've been looking at tonight, I generated using this NASA Solar System Trex portal system. And this is something that you can do yourself. This wonderful software is something you don't buy anything, you don't install anything. It's all browser based. You just point your browser to trek.nasa.gov, click the Explore Treks button, and you'll get this menu of a growing number of worlds. We're going to continue adding to this, but worlds that you can explore in varying degrees of detail. Certainly for the worlds that we've had missions that have orbited those worlds for a long time, we have a comparatively large amount of data. In worlds that we just did flybys of, such as the moons of Jupiter and Saturn, the data is much more fragmentary. But still, we are putting together an impressive catalog. Now, these portals are designed for actually mission planning and for conducting planetary science, but they're also excellent tools for amateur astronomers, for the general public, for citizen scientists, for students. And I'll give you a little bit of a view of how they work. So we'll start out with our Moon Trek portal, and it's essentially a GIS system for the moon. Like any good GIS, you can pan, you can zoom. So here we'll zoom down to the crater Tycho, and one of the first things a student might ask is, how big is it? Well, measuring a distance is as simple as drawing a line. So here we'll just draw a line from one edge to the other of Tycho. We can see that it's 83 kilometers across. That's a big hole in the ground. Now, one of the other things you might then ask is, well, how deep is it? And again, that's as easy as drawing a line. So we have an elevation profile tool. Now we'll draw a line again. We'll extend it a little further on either side so we catch the rim. But here we'll submit, and you can see how you get a nice elevate. We'll move Tycho off to the side there so we can see this. You get a nice elevation profile. So you can measure the heights of mountains, the depths of craters and valleys very simply. That's pretty cool. Another thing you can do is you can draw a bounding box around any piece of terrain that you want. So we'll draw a bounding box here around Tycho, and it'll give you a choice to generate either an STL or an OBJ file to send to your 3D printer. So you can make 3D prints of any terrain that you like. Another fun feature is you can use your mouse to draw a path anywhere you want across the surface. And then the Moon Trek or Mars Trek or some of the other treks will return to you a QR code. Scan that QR code into your smartphone and then put your smartphone, either iOS or Android, into a cheap $5 Google Cardboard compatible pair of goggles, and you will fly whatever path you drew in virtual reality. That's a lot of fun. This is a custom virtual reality experience. But the most fun is you put it in interactive 3D mode, and you can just go flying across the surface interactively. It's probably going to look a little jerky here going across Zoom, but from home, if you've got a good internet connection, this can be nice and smooth. You can rove across the surface, fly across the surface. It's a wonderful way to go exploring. So I encourage you to go to trek.nasa.gov and explore the solar system. I want to give thanks here to the development team. So this is a team I lead at NASA, and the development team down at JPL, my co-lead Emily Law, Sean Malhotra, our lead engineer, and a fantastic development team that has put together these amazing tools. So with that, if I haven't put you all to sleep, I will gladly take any questions you might have. So
thank you very much. That was fantastic. Yes, we are open for questions, and feel free to unmute yourself and speak your question, or if you prefer to raise your hand or type into the chat, I can get you that way too.
This is Mary, and I noticed that on so many of these moons, the oceans are below the surface. Does anybody speculate why our oceans are on the top?
Well, one of the things that works to our advantage is we have a nice thick atmosphere. Those moons do not. And that atmosphere allows liquid water to actually exist on the surface. If we didn't have that atmosphere, then they would just boil away into the vacuum of space. So in the case of these moons that are out there further away from the sun, they're far enough out that water is going to be a much more common constituent than it is here in the hot inner solar system. So it's not surprising to find ice.
Mm-hmm.
What we think is happening is that we're having gravitational resonances between the moons and tidal forces exerted by the planets that they are orbiting, causing a kneading of the rocky cores of these moons. And that, imagine the cores, because of the tide, stretching. And as it stretches, you get heat generated. And that heat could actually cause some sorts of geothermal or hydrothermal vents on the floor that would cause melting of the ice. Also, the tidal friction that is generated by resonances with other moons or by the orbit around the parent body could also generate heat. And also you can have radioactive decay within the cores of the moons. All of that can generate heat that could melt some of that ice above the rocky core, but below that frozen crust.
Got it.
That's an
Thank
excellent question.
Okay.
Yeah, I'll ask a question. I loved your presentation, and what an amazing program. It's really fascinating.
Yeah.
So when you showed the view of Olympus Mons from the side, the profile of Olympus Mons, and the gravity on Mars, I think, is about 1/4 of the gravity on Earth or something like that.
About a third, yeah.
Yeah. So I expected such a high mountain to be more dramatically pointed, but it looked quite gentle slopes going to the top of that extremely high mountain. So I was kind of shocked when I saw that. So
Yes.
tell us about why isn't it steeper than I would think it should be?
So in general, that's an excellent question. And in general, we see Martian volcanoes as being these very broad shield volcanoes. Now we see here on Earth, we see very broad shield volcanoes. And then we also see very steep-sided composite volcanoes. Now, the shield volcanoes are often associated with areas of, well, like in the case of the Hawaiian Islands, mantle hotspots, where you have basaltic lava, basaltic magma, essentially, coming up and punching through the crust and forming these volcanoes. Now, basalt has a low silica content, which means it has a low viscosity. And so it's thin and it's runny. And so when you go to the big island of Hawaii and you look at Mauna Loa, it's this big, broad, low shield. If you drive up to the top of Kilauea volcano in Hawaii Volcanoes National Park, you can look down into the caldera, but you don't get a sense of standing on a tall mountain because it's such a broad, low, gradual climb. if you're in the city of Hilo and you look across Hilo Bay at the big broad shield of Mauna Kea, same thing. So what we have there are examples of basaltic, low silica content lava, causing very low viscosity and therefore volcanoes that spread out over low profiles. On the other hand, here on Earth, we also have very steep volcanoes. Things like, well, go down to the Andes and those steep volcanoes of the Andes, or here in the Cascade Mountains, Northern California and Oregon and Washington. But what we have happening there is a very different process. There we have a process of plate subduction, plate tectonics, where one plate is riding over the top of another and a plate is diving down. And the material of that diving plate, which has been enriched in all kinds of sediment and water and all kinds of other things, ends up being more silicate enriched. And so it comes up, when it punches up through that overriding plate, it is thicker and pastier. And if you go up to like Lassen Volcanic National Park, you can see volcanic features that almost look like toothpaste that has been squeezed up out of a tube. This is not thin, runny stuff. This is thick, silicic lava that is typically associated with plate tectonics. On Mars, we do not seem to have plate tectonics. So as a result, we don't see those steeper volcanic cones that here on Earth we would associate with plate tectonics. Instead, we see the broad, low basaltic, low viscosity types of volcanoes. For the most part, there may be a few interesting exceptions, but that seems to be the rule on Mars. It seems to be because of a lack of plate tectonics on Mars. Another great question. Thank you, Tom.
Well, I was curious if you might know offhand, are the 2 Martian moons in the catalog?
So we actually are currently working on a Phobos Trek portal. We're doing that in conjunction with the Japanese Space Agency, JAXA, which is planning its MMX mission, the Martian Moons Explorer mission. And so we are working with them on that. And so keep an eye on Solar System Treks. As I said, we're continuing to add new worlds, and Phobos is definitely among them. We actually have much better data to work with on Phobos than we do Deimos right now. So we're going to concentrate on Phobos first.
Do these virtual maps come entirely from orbital probes, or are they also from surface landers?
So in general, we got our best data from orbital probes. In some cases, we have not been able to do that. In some cases, all we've done is flybys. You know, I'd love to do a Pluto trek. We never orbited Pluto. Yeah. We did a quick flyby. At some point, I think you will see a Pluto trek. But when you do, what you will see is you'll see one side of Pluto is going to be much higher resolution than the other side. Because as we approached, we had a distant view of one side. And as we got closer, Pluto turned and we got, you know, a much better view, you know, of a more detailed view of the site that we did our close pass of. So, in the case of the moons of Jupiter and Saturn, to date, we have never orbited any of those. We just did flybys. And so you'll notice that in those cases, the data we have is much less rich, much less detail than what we have amongst the worlds that we were able to really linger around and orbit and get long, prolonged detail that, quite frankly, is a lot more satisfying. But those places that we did flybys of, those are really fascinating teases. And so we're looking forward to getting much better, more detailed views in missions to come.
Did I remember you mentioning that you could tell what the composition of some of these areas were, what the mineral composition was?
Yes. So when you look at something like Moon Trek, you have literally thousands of different data layers you can choose from. So you can view the moon through the eyes of many, many different instruments aboard a wide variety of spacecraft. And that includes mineralogy. The same thing with Mars. And so we can take a look at mineralogy maps and geologic maps. You can look at gravity maps. You can look at all kinds of things. So the moon we have really, that's the one we have in most detail. And like I say, there are literally thousands of different data layers for you to choose from.
I will ask one more question about approaching Mars with a spacecraft. My thinking is that it seems like, especially a manned mission to Mars, that it would make a lot more sense to establish a base on Phobos because of the gravitational simplicity in comparison to landing and taking off from Mars itself. And then on the other part of the question is, has there been any discussion about space elevator concept being used on either the moon or Mars because of the same complication of landing and taking off again, especially for manned missions?
Yes, absolutely. And especially in the case of Mars. Landing on the surface of the moon is actually comparatively easy as opposed to landing on the surface of Mars or coming back to the Earth. Because you have this whole problem of EDL, entry, descent, and landing, and that entry part, coming in through the atmosphere. You're coming in at high speed, and essentially you come in as a fireball. That you've heard the term 7 minutes of terror when it comes to getting down to the surface of Mars. Going from the Earth to Mars, you need a big kick of delta V. You need a big push. You need to go at high speed. And you come into Mars at a high speed. And that makes for a challenging, technically complex landing. Landing on Phobos is much easier. But Phobos, being in a very low orbit around Mars, provides an excellent opportunity to view Mars in detail, but as you say, to land quite easily in comparison. There's a good chance that we might find Martian material on Phobos. Mars has been bombarded by meteoroids and asteroids, and material has been blasted off the surface of Mars, and some of that has doubtless landed on Phobos. so we could collect it there. But Phobos could actually be just a natural space station for us in orbit around Mars. And yes, indeed, as you mentioned, people are looking at the possibility of a space elevator. The gravity environment and the atmospheric environment is a little more conducive to that type of thing than we would see here on Earth. So that's a very interesting possibility that people are looking at. So yes, absolutely. It's in both cases, it's a great idea, Tom.
Are there any other questions?
Well, I think we're good.
Yeah, I think so too.
Well, I want to once again thank you for letting me talk to you again. It has been a pleasure. I always enjoy time spent with the SFAA. It's a wonderful group. And gee, I look forward to seeing you all in person again sometime in the
I do too.
Don't we all?
Yes, indeed. Thank you so very much. It's wonderful. I hope we've inspired people to go to trek@nasa.gov.
Excellent presentation.
Yeah.
Thank you so much.
Thank you. Thank you very
Thank
much.
you. Thank you everyone for coming as well.
All right.
And
Jean-Pierre.
if we could post the web address for that program you created.
Oh yeah, what was that one more time? I want to type that into my browser.
That's
Trek.
https://trek, that's trek.nasa.gov. And one of the things you'll find too is that when you go into any of the portals on the Trek site, the first thing it will ask you is if you want to have a tutorial, essentially a guided tour through the various controls. Probably your first few times in, your answer should be yes, and it'll help you ease you through the process of learning how to fly around with the Trek portals.
All right, wonderful.
Thank you.
Well, thanks again.
Thank you
And
so
Thank you
very
very
much.
Thank you. You all have a good evening.
You too.
Same. Bye-bye.
Thank you.
Thank you.
I'm so glad that it's being on, that it will be on our lecture archive, so people
Definitely.
can go back and see it again and again.
Thank you. Have a
Thank
good night.
you.
Thank you.
Bye.